Hello. In this WAGO tutorial, we'll guide you through adding charging points in WAGO Load Management and delve into the various configuration possibilities. We're using a charging park simulation, which runs as a Codesys 3.5 visualization on a PFC 200. In the same network, there's a CC100 installed with WAGO Load Management, licensed for 5 charging points. The simulation includes 3 meters for grid connection, PV system and building, along with 5 charging points. As the simulation is running on a PFC, all meters and charging points share the same IP address and are addressed through ports in this example. In a real system, however, you'd have different IP addresses since each meter or charging point typically acts as a network participant. In the WAGO Load Management tutorial part 2, we added meters and briefly set up charging points without going into detail. Here, we begin at the dashboard and will edit all 5 charging points to demonstrate the step-by-step configuration options available to you. By clicking on the pencil icon, you can open the edit window for the charging point. Names and descriptions have already been allocated. To keep your charging points and meters in alphabetical order on the dashboard, it's recommended to start names with a number. Through WAGO Load Management, charging point data can be forwarded via MQTT or as a Modbus TCP server, as we'll detail further in another tutorial. The device type list shows all compatible wall boxes with the specified firmware version for this version of the WAGO Load Management. Hence, ensuring your charging point's firmware version matches the load management version is crucial. Compatibility lists are available on the WAGO Load Management webpage, linked in the video description. In our scenario, we're using a Heidelberg energy control with firmware 2.6.4 and Modbus, alongside WAGO Load Management version 2.18.0. For some older wall boxes, an internal meter may not be included, requiring an additional external meter. In such cases, set up the meter as a consumption meter and link it to the wall box via this field. Therefore, only pre-established meters are included in the drop-down list. However, the Heidelberg wall box provides meter data, allowing us to set this field to no meter. The minimal charging current denotes the threshold beyond which the charging point shuts down. The maximum charging current is the highest charging current supplied at a charging point, which can vary among charging points. Next, determine whether the charging point operates single, 2 or 3-phased and specify the connected phases. Following this is the phase rotation, offering options like 0 degrees, 120 degrees, 240 degrees and their reverse counterparts. A brief explanation. Multiple wall boxes are typically phased rotationally connected. Hence, the first wall box connects to L1, L2, L3, the second shifts one phase to connect to L2, L3, L1, and the third shifts 2 phases to connect to L3, L1, L2. A fourth box connects again to L1, L2, L3, and so on. This distributing the load across 3 phases when multiple vehicles charge single-phased, reducing phase imbalance. Do not wake car from hibernation. Often, a fully charged vehicle remains connected to the wall box for a period. If this lasts a while, the vehicle's battery might self-discharge slightly, prompting the vehicle's load management to initiate another charging cycle. To prevent this, check the box allowing the vehicle to remain in a rest state following successful charging, needing reconnection to charge again. Charging points can be prioritized differently, affecting both maximum charging capability and shutdown order when insufficient charging power is available. To demonstrate, we assign charging point 5 a priority level of 3. We then switch to the simulation and gradually reduce available power by increasing building consumption. Once the maximum current consumption of 100 amps is reached, WAGO Load Management appropriately reduces full charging power and specific charging points receive less power. However, due to charging point 5's higher priority, it continues to charge at full strength. Further raising consumption forces some charging points offline as they can't sustain minimal charging current, but charging point 5 remains fully operational. Only once all other charging points shut down will charging point 5 diminish as consumption keeps dropping. Communication in charging parks is generally executed using two standards: Modbus RTU and TCP and OCPP. OCPP, or Open Charge Point Protocol, addresses communication needs with charging stations, offering RFID management and backend connections for billing, unlike Modbus. To delve deeper, we must first understand different charging park types and their respective communication structures. We'll begin with the public charging park, where charging stations connect directly via OCPP to the backend, the billing system. If connecting to a dynamic load management system, Modbus TCP is used, requiring charging stations capable of handling both OCPP and Modbus TCP. Another option involves routing the backend via WAGO Load Management, accommodating charging points not compatible with Modbus. In this case, charging stations are linked to dynamic load management using OCPP, serving as a proxy and forwarding station data via OCPP to the backend. In private charging parks, where billing systems aren't required, all accessible communication protocols may be used, barring preference for RFID-based user management, necessitating OCPP connection as previously mentioned. An OCPP connection mandates an NTP server and a DNS server for stable connections. Additionally, with OCPP and load management usage, free charging functionalities like free mode, free charging and free vending should be disabled in charging stations to enable load management. During setup, the OCPP connection is configured in the charging points and each assigned a unique charge point ID, with stations having multiple points identified by connector ID. Accordingly, entries are made in WAGO Load Management. We recommend Modbus TCP startup via DHCP and a later transitioning to static IP addresses for operation. Modbus RTU supports up to 16 participants and demands a 120 ohm resistor at each end, pre-built into the CC100's interface. Having explained nearly all aspects and fields of charging point configuration, a charge point ID at the top becomes relevant for formula usage. Concluding, we'll demonstrate setting up charging groups, typically necessitated when a park segment holds separate protection via an additional distribution and doesn't access full grid connection power. Initially, create all charging points as done with R5. Via the top right button, open the new charging group window, provide a name and description, then select charging points for this group or connected to the sub-distribution. But why add meters to a group? Examining setup clarifies. You can specify a maximum total current, like 25 amps, and a separate maximum charging current. This accommodates other consumers or power producers, like a building with a PV system sharing the sub-distribution, hence metered. A charging group thus functions as both an isolated section of the park and an independent subordinate management hub. Additionally, charging groups can be nested. Hence, linked to this sub-distribution park is another secured at 16 amps, for which you can create a charging group, then select the appropriate superior group here. In our simulation, the initial two charging points are limited to 25 amps total and charging current. The dashboard now displays the group. When full power is granted in simulation, charging points 3 to 5 draw 16 amps, while points 1 and 2 share the group's 25 amps. If one car disconnects, the remaining one charges at maximum power. And that concludes the tutorial on adding and configuring charging points and groups in WAGO Load Management. Please leave us a thumbs up if the video was helpful, subscribe to the channel, and contact the WAGO Support Center if you have any questions.